1899. Baldwin Locomotive Works, Philadelphia. The foundry floor shook as 50 tons of molten iron poured into sand molds shaped like massive cylinders. Through the coal smoke and hammer blows, a 280 Consolidation took form, built not for speed or elegance but for the brutal work of hauling freight across America's expanding rail network. No one called it revolutionary. Baldwin's engineers simply scaled everything up. Boiler plates an inch thick instead of 3/4, driving wheels cast from solid steel instead of lighter alloys, valve gear machined with clearances measured in sixteenths rather than thousandths. The locomotive weighed 140 tons empty, 20 tons heavier than competing designs, and cost the railroad nearly $12,000, a fortune at the turn of the century. Railroad superintendents considered it just another workhorse. Break it in for a year, run it hard for 20, then scrap it when maintenance costs exceeded its value. That was the economic reality of steam power in 1899. Machines wore out. You replaced them. Progress marched forward. Yet in 2015, Locomotive 47 of the East Broad Top Railroad steamed past its 116th birthday, pulling tourist trains through Pennsylvania coal country with a reliability that baffled modern mechanical engineers. Its boiler held pressure better than when new. Its cylinders delivered smoother power than they had in 1920. Its valve timing, untouched since a 1947 rebuild, remained so precise that crews could predict its behavior to the second. The contradiction demanded explanation. Modern diesel-electric locomotives, built with metallurgy and engineering that made 1899 technology look prehistoric, rarely survived 40 years without major rebuilds. Computer-controlled systems failed. Fuel injection pumps wore out. Electronic governors needed constant replacement. But this century-old steam engine kept running, not despite its age, but seemingly because of it. The more it worked, the better it performed. Like a cast-iron skillet that cooked better after decades of seasoning, the Baldwin had somehow improved through use rather than degraded. The physics shouldn't have allowed it. Metal wore. Components fatigued, everything eventually failed. Tom Morrison ran his hand along the locomotive's driving rod, feeling the oil-smooth surface of steel that had been hammering back and forth 300 times per minute for over a century. He directed mechanical operations at the East Broad Top, where 4 Baldwin Consolidations, all built between 1899 and 1914, remained in daily operation serving tourists who paid to experience authentic steam railroading. "She pulls harder now than she did 30 years ago when I started," Tom said, watching as 47's crew prepared for the morning run. "Boiler inspector measured her last month. Thickness still exceeds original specifications in most places. 116 years old, and the metal's thicker than when Baldwin delivered her." His assistant, Sarah Chen, checked her thermal imaging camera as the fireman brought the boiler pressure up to 180 pounds. "That's impossible. Metal doesn't grow, it erodes." Tom smiled and pulled a maintenance log from 1923. "That's what modern engineering says, but this engine missed the memo." Sarah climbed into 47's cab as morning light broke across the roundhouse. The brass gauges glowed in the firebox light. Steam pressure, water level, boiler temperature, all reading steady. The locomotive had been in steam for 2 hours, bringing pressure up slowly as regulation required, and the engine breathed with a rhythm that seemed almost alive. "Watch the crosshead when we start moving," Tom instructed from the ground, gesturing toward the massive steel assembly that converted the piston's back-and-forth motion into rotary power at the driving wheels. "You'll see what I mean about the wear patterns." Sarah had spent 3 years studying mechanical engineering at Penn State before joining the railroad. Her education taught her that moving parts wore against each other, creating clearance and slop that degraded performance. Bearings needed replacement. Surfaces needed machining. Precision eroded with every cycle of operation. The engineer notched the throttle open. Steam rushed into cylinders 22 inches in diameter, driving pistons that pushed 200 horsepower through connecting rods as thick as telephone poles. The locomotive eased forward with a smoothness that Sarah hadn't expected from a machine older than powered flight. "Feel the crosshead guide," Tom said, having her place her hand near the polished steel surface that kept the piston rod tracking straight. "No vibration, no play. That's 116 years of metal sliding against metal, millions of cycles, and it moves smoother than most modern machinery. Sarah pulled out her dial indicator and measured the crosshead clearance, 0.03 of an inch on each side. She consulted the locomotive's original Baldwin specification sheet, yellowed with age but perfectly legible. Original clearance, 0.05. That can't be right, she said, checking her measurement again. The clearance got tighter? That means the metal grew back, or the surfaces work hardened and wore in instead of wearing out, Tom finished. Now check the cylinder walls. Inside the front cylinder, accessible through an inspection port, Sarah ran her fingers across steel that felt glass smooth. No scoring, no pitting. Just a mirror finish that reflected the light from her inspection lamp. The original Baldwin drawings specified cylinder walls machined to a surface finish measured in thousandths of an inch. This surface felt smoother than ground steel. Tom showed her borescope images from 5 years earlier, then from 10 years before that. The cylinder bore actually showed improvement over time, not degradation. The metallurgist from the Smithsonian couldn't explain it either, he said. Sent samples to 3 different labs. Best theory they had was something about grain structure alignment under stress. The morning run departed with 47 pulling 6-passenger cars up the 2.8% grade to Colgate Grove. Sarah monitored the locomotive's performance, drawbar pull, steam consumption, speed, comparing it to historical data from the 1940s when the railroad still hauled commercial coal. Every metric showed the same impossible pattern. The engine worked better now than it had 70 years ago. Not just good for its age or surprisingly capable, actually better. Measurably, documentably better. Modern locomotives don't do this, Sarah said as they rolled back into the station. Why does this one? Samuel Vauquelin never believed in building locomotives to minimum specifications. As Baldwin's chief engineer from 1886 to 1919, he followed a design philosophy that seemed wasteful to efficiency-minded competitors. Make everything twice as strong as calculations required, then add a safety margin. The 1899 Consolidation embodied this approach in every component. Tom spread original Baldwin engineering drawings across his office desk, showing Sarah the specifications that governed 47's construction. The boilerplates measured 1 inch thick. Standard practice for the era called for 3/4. The firebox crown sheet, the most stressed component of any steam locomotive, was built from double-riveted steel plates with stays spaced closer than engineering tables demanded. Vauquelin calculated stress loads, then doubled them, Tom explained, pointing to handwritten notes in the margins of the century-old drawings. He assumed the worst possible conditions: bad water, careless firing, maximum load-up, maximum grade. Then he designed for those extremes as if they were normal operation. The cylinders told the same story. Cast iron walls measured 3 inches thick where competing designs used 2. The piston rods, solid steel forgings 4 inches in diameter, were massive compared to the hollow designs other builders favored. Even the valve gear, the complex mechanism that timed steam admission to the cylinders, used components scaled up beyond apparent necessity. Sarah ran stress calculations on her laptop, inputting the actual dimensions from Baldwin's drawings. These cylinder walls could handle pressures 3 times what the boiler produces. Same with the piston rods. They're over-engineered by a factor of 4. That's the point, Tom said. Vauquelin knew metal fatigued. He knew thermal cycling weakened structures. He knew railroad maintenance was inconsistent at best. So he built in margin that let the locomotive survive abuse that would destroy a modern machine. The driving wheels demonstrated the philosophy perfectly. Each wheel measured 50 inches in diameter and weighed 2,800 pounds, cast from a single steel ingot at Baldwin's foundry. Modern locomotive wheels used lighter alloys and complex hub designs to reduce weight. Baldwin's approach was brutally simple: use more metal. The bearing journals, the precisely machined surfaces where the wheels rotated in their supporting frames, received similar treatment. Standard practice called for journals 9 inches in diameter. Baldwin made them 10. The additional inch of diameter increased the bearing surface by over 20%, spreading loads across more metal. Here's what's interesting, Tom continued, pulling out metallurgical reports from the 1980s when the Smithsonian studied the East Broadtop's locomotives. These overbuilt components developed characteristics nobody anticipated. The extra metal mass acted as a heat sink, preventing the thermal stress that cracked lighter designs. The oversized bearings ran cooler, which meant better lubrication, which meant less wear. Baldwin had essentially built a locomotive with so much material buffer that normal wear couldn't reach the structural core. Like a bar of soap used for years that still had inches to go, 47's components had margin to spare even after a century of service. "They accidentally built something that got better with age," Sarah said, studying the drawings. "The overbuilding created conditions where work hardening and wear-in could happen without compromising strength. The transformation happened slowly, invisibly, across decades of daily operation that no single person witnessed in full. But the accumulated evidence told a story of metallurgical evolution that modern material science was only beginning to understand." Tom showed Sarah the boiler's interior during the annual inspection, a ritual required by federal law for any steam vessel operating under pressure. The inspector, Dave Martinez, had been examining locomotive boilers for 30 years and knew what deterioration looked like. This wasn't it. "Run your hand along the crown sheet," Dave instructed Sarah, pointing to the curved steel surface that formed the top of the firebox. "Tell me what you feel." The metal felt smooth, almost glassy. Sarah had expected rough scale, the calcium and mineral deposits that accumulated in any boiler using natural water. Instead, she found a thin, uniform coating that flaked away easily to reveal steel underneath that looked decades younger than it was. "That's magnetite," Dave explained. "Iron oxide in its most stable form. It builds up in layers over time, and if the water chemistry stays consistent, it actually protects the underlying metal, acts as a barrier against corrosion." He pointed to measurement marks on the steel. "We ultrasound test thickness every year. This section is reading 0.98 inches. Original specification was 0.95. Sarah looked confused. "The metal got thicker?" "The magnetite layer added measurable thickness," Tom clarified. "But underneath, the steel erosion rate is basically zero. The boiler seasoned itself like cast iron cookware. The more it ran, the better the protective layer became." The phenomenon extended beyond the boiler. In the cylinders, where superheated steam at 400 degrees Fahrenheit slammed, pistons back and forth 300 times per minute, the cast iron walls had developed what metallurgists called a work-hardened skin. The surface grain structure had been mechanically compressed and aligned through billions of cycles, creating a layer harder than the core material. Tom produced cross-section samples from a scrapped sister locomotive, showing Sarah the difference under magnification. The outer 1/8 inch of cylinder wall showed a grain structure distinctly different from the interior, denser, more uniform, with crystal boundaries aligned in the direction of stress. "It's like forging," Sarah said, recognizing the pattern from her materials science classes. The repeated impacts aligned the grain structure, made it stronger. The valve gear told perhaps the most remarkable story. The complex assembly of eccentric rods, links, and pivot points had worn together into such precise fit that their timing remained accurate to within 2 degrees across the full range of operation. Engineers called it wearing in, the process where mating parts gradually achieve better fit through use than machining alone could provide. Tom demonstrated by manually rotating the driving wheels, watching the valve motion. "Stevenson valve gear from 1899, never been rebuilt, just maintained. The pivot points have maybe 1,000th of play after 116 years. Modern locomotives need valve gear overhauls every 15 years because the clearances open up. This got tighter." The seasoning process had created something Baldwin's engineers couldn't have predicted, a locomotive that improved through use. Philadelphia's Baldwin Locomotive Works sprawled across 20 city blocks in 1899, an industrial cathedral where 8,000 workers transformed raw materials into finished locomotives at a rate that amazed international observers. Matthias Baldwin had founded the company in April, but by the turn of the century, his successors had refined production to a precision that rivaled European craftsmen while maintaining American industrial efficiency. Tom walked Sarah through historical photographs displayed in the Roundhouse office, showing the scale of Baldwin's operation at its peak. They built 17 locomotives per week in 1899. Not simple machines, complete, tested, ready-to-run power plants on wheels. Each one documented, each one inspected, each one backed by Baldwin's reputation. The photographs showed craftsmen hand-fitting valve gear, boilermakers riveting steel plates, pattern makers creating the sand molds that would shape molten iron into cylinders and wheels. This wasn't mass production in the modern sense, it was systematic craft work scaled up to industrial capacity. Samuel Vauquelin's influence permeated every aspect of production. He had started as an apprentice machinist in 1869, working his way up through practical experience rather than formal engineering education. That hands-on background shaped his design philosophy. Build what you know will work, not what calculations say might work. Vauquelin tested everything to destruction, Tom explained, showing Sarah a 1902 technical paper where Baldwin documented cylinder failure modes. They built test cylinders, ran them at double pressure until they cracked, then redesigned to eliminate the weak points. The 1899 Consolidation incorporated 10 years of failure analysis. The company's material specifications reflected this empirical approach. Baldwin sourced iron from specific Pennsylvania foundries whose metallurgy consistently produced castings with favorable graphite distribution. They aged cylinder castings for 6 months before machining, allowing internal stresses to relieve naturally. Boilerplates came from mills that could document their steel-making process down to furnace temperature and cooling rates. Sarah examined a Baldwin material specification sheet from 1899, a document that specified chemical composition, grain structure, tensile strength, and impact resistance for every major component. This is more detailed than some modern specifications I've seen. Baldwin knew their reputation rode on reliability, Tom said. A locomotive failure could shut down a railroad. A boiler explosion could kill a crew. They couldn't afford shortcuts, so they built in quality that seems extravagant now but was essential then. The assembly process emphasized fit and finish. Bearing surfaces were hand-scraped to ensure even contact. Valve gear was individually adjusted and tested under steam before the locomotive left the erecting shop. Each machine received a test run on Baldwin's private track, pulling loaded cars to verify performance before delivery. The company documented everything in bound maintenance manuals that accompanied each locomotive, exploded diagrams showing every component, parts lists with Baldwin part numbers, maintenance schedules, lubrication specifications. They expected their machines to be serviced by railroad mechanics far from Philadelphia, so they provided the information necessary for long-term maintenance. That's why we can still maintain these locomotives, Tom concluded. Baldwin gave us a complete engineering package, not just a machine. They expected these to run for decades. Sarah pulled up reliability data on her tablet, comparing the East Broad Top's Baldwin locomotives to modern heritage railroad equipment. The statistics told a story that contradicted everything she had learned about technological progress. The Virginia and Truckee Railway's 1916 Baldwin 280 logged 12,000 operational miles in 2014 with 0 unscheduled shutdowns. Their 1952 Alco diesel electric, built with 50 years of technological advancement over the Baldwin, managed 8,500 miles before a generator failure sidelined it for 6 weeks. Tom had compiled similar data from dozens of heritage railroads across America. See the pattern? The steam locomotives, when properly maintained, run more reliably than equipment built. Decades later, it's not nostalgia, it's measurable performance. The contrast became stark when examining specific failure modes. Modern diesel-electric locomotives depended on electrical generators, traction motors, electronic controls, and fuel injection systems, all components with defined service lives. A typical diesel might need generator rewinds every 15 years. Traction motor rebuilds every 20, and complete control system upgrades every 25. The Baldwin required boiler work every 15 years under federal mandate, but the work remained straightforward. Replace worn tubes, inspect stays, patch thin spots. The core components, cylinders, wheels, frames, essentially lasted forever if protected from collision damage. Durango and Silverton runs 3 Baldwin narrow-gauge locomotives from the 1920s, Tom continued, showing maintenance records. Together they log over 100,000 miles per year hauling passengers. Their modern diesel switcher does maybe 5,000. The Baldwins are the primary fleet because they're more reliable. Sarah examined the economic analysis. Each steam locomotive required a skilled crew, engineer, fireman, sometimes a helper, while a diesel needed only an engineer. Labor costs favored diesel. Fuel costs also favored diesel, but when factoring in rebuild costs and unscheduled downtime, the steam locomotives showed surprising economic resilience. "Here's the real difference," Tom said, pulling up photos of a disassembled diesel locomotive. "When a diesel breaks, you're often waiting for parts. Electronic modules, specialized injectors, custom generators. Some components come from overseas with 6-month lead times. The railroad sits idle." He contrasted this with the Baldwin's repair philosophy. Everything on a steam locomotive can be rebuilt locally. Cylinders can be resleeved, boiler tubes are standard sizes. Even a cracked frame can be welded. We don't depend on manufacturers who might not exist anymore. The Cumbres and Toltec Scenic Railroad proved the point dramatically. When their diesel-electric helper locomotive failed in 2012, repair quotes exceeded $200,000 and required 6 months. They pulled a 1925 Baldwin out of static display, performed a basic inspection, and had it hauling freight within 3 weeks for less than $15,000. "That Baldwin hadn't run in 30 years, Tom said. "They fired it up, checked the basic systems, and it worked. Try that with a modern locomotive that's been sitting for 30 years. Sarah watched as 47 pulled into the station, completing its 10th trip of the day without incident. "So the simplicity is the advantage?" "The simplicity and the overbuilding," Tom replied. "Together, they created a machine that outlasts everything that came after it." The dynamometer car sat coupled behind locomotive 47, its instruments recording every measurable aspect of the engine's performance. The Smithsonian Institution's Railroad Technology Division had sent their team to document what their preliminary studies suggested: a century-old locomotive performing beyond its original specifications. Dr. Robert Chang examined real-time data on his laptop as the locomotive accelerated up the grade. "Drawbar pull is reading 28,400 pounds at 15 miles per hour. What did Baldwin rate this engine for?" Tom consulted the original specification sheet. 25,000 pounds at 15 miles per hour. She's exceeding factory rating by 13%. The testing continued throughout the day, pulling tests at various speeds, thermal efficiency measurements, steam consumption analysis, valve timing verification. Each metric was compared against Baldwin's 1899 performance guarantees and against historical data from when the locomotive was newer. The results were undeniable. Cylinder efficiency had improved from 82% when new to 87% after a century of operation. Steam consumption per horsepower hour had decreased by 9%. Tractive effort, the actual pulling force at the wheels, exceeded original specifications across the entire speed range. "The metallurgical changes we documented explain most of this," Dr. Chang said, reviewing his team's analysis. "The work-hardened cylinder walls improve steam sealing. The seasoned boiler delivers more consistent steam quality. Even the worn-in bearings reduced friction losses." But the most remarkable finding came from valve timing measurements. The Stevenson valve gear, untouched except for basic maintenance since 1947, delivered steam admission and release timing within 1 degree of optimal across all cutoff positions. Modern steam locomotives, even after professional rebuild, rarely achieved such precision. Sarah had documented parallel tests on 2 other Baldwin Consolidations at the East Broad Top, one from 1911, another from 1914. Both showed the same pattern of improved performance with age. The phenomenon wasn't unique to Locomotive 47. It represented fundamental characteristics of Baldwin's overbuilt design philosophy. "Here's what I think happened," Dr. Chang concluded, addressing the assembled railroad staff and Smithsonian team. "Baldwin accidentally created conditions for beneficial metallurgical evolution. The oversized components ran cooler and at lower stress levels than minimum spec designs. This allowed work hardening, grain structure alignment, and protective oxidation to improve the base materials rather than degrade them." He displayed microscopic images of cylinder wall samples, showing the dense, aligned grain structure. This didn't happen overnight. It took decades of thermal cycling and mechanical stress to develop, but once established, it created a surface harder and more durable than the original cast iron. Tom watched as 47's crew prepared the locomotive for its evening run. The engine that Baldwin delivered in '89 as a capable freight hauler had evolved into something better, not through technological upgrading, but through a century of use that refined its metallurgy and refined its precision. They built it so strong that time made it stronger, he said. And that's why it's still here while everything built to replace it is gone. The locomotive's whistle echoed across the valley as steam pressure built for the final run of the day, a sound unchanged since 1899, delivered by a machine that had improved with every mile traveled across 116 years of American railroading.